Okay, welcome back, Chapter 4. Now we're actually going to be able to, so the process is we need to get we need to find the critical numbers, and then we'll have this first derivative test that will tell us whether we have a max or a min or neither. Okay, and the first thing we'll look at, because eventually what's going to happen is, if you look at this graph, where do you think the maxes will be? Well, there'll be one here, and then a min here, and maybe a min here. And if you look at the tangent lines at those places, those are the places where the derivatives equal to 0. And we know that the relative maxes and mins occur at critical numbers, and that's going to be places where the derivative is 0, also where the derivatives doesn't exist, but for the most case, it's where the derivative is equal to 0. If you look around those places, you'll note that on this side the graph is increasing, and then on this other side the graph is decreasing. Okay? So we're going to do kind of an analysis. We'll label the critical numbers, right? So there'll be maybe C1 here, C2 here, C3 here, and then on either side of them we'll want to know whether the function is increasing or decreasing, because if it goes up and then down, there's going to be a max. Okay? If it goes down and then up, there's going to be a min, and then if it goes up and then down again, there's a max. Okay, so by looking at the derivative, we'll be able to make these conclusions, because the derivative is really just another way of talking about slope. And you think about the slope of any tangent line to the curve, and kind of these intervals here, the slopes are always positive. In other words, you have a positive slope, it's going up. Okay, so that's where we're headed. Okay, that's the big picture. All right, so first we want to start by kind of talking about increasing versus decreasing. And we want a more rigorous definition than just looking at the picture and saying, oh, it's going up and oh, it's going down. Okay, so definitions. So first for increasing, if x1 is less than x2, then guess what? F of x1 will be less than f of x2. So it's going up. Secondly, decreasing. In this case, if x1 is less than x2, then f of x1 will be above f of x2, like that. Okay. Okay, that's really it. So now we have, we're going to relate the derivative to this idea of increasing and decreasing. That turns out to be theorem 4.5. So given f is continuous on the interval from a to b, and we're going to say an open interval, given f, oh sorry, no, on the so given f is continuous on the closed interval from a to b, and differentiable on the open interval from a to b, the open interval from a to b, then if the derivative is positive, it means the function is increasing. So if f prime of x is greater than 0 on a to b, then f of x is increasing on the interval from a to b. Okay. If the derivative is negative on a to b, then f of x is decreasing on a to b. And then if f prime of x is equal to 0 on this interval, it's constant. So it has a 0 slope, right? Okay, we could prove this, and it comes from the mean value theorem. Okay, so we might as well take a look at the proof. And consider the first case. where f prime of x is equal to 0. Here we use the mean value theorem because this function satisfies the continuity and the differentiable criteria of the mean value theorem. Okay, so we can apply the mean value theorem to this interval and say there exists a c-value between pretty much any x1, x2 in this interval such that the slope of the secant line from x1 comma f of x1 to x2 comma f of x2 is equal to the derivative of the function at that point c. Okay. We know, or we'll suppose, x1 is less than x2. Okay, and in that case, it forces the numerator to be then a certain way. Okay, because f prime of x is greater than 0 in this interval, we know that f prime of c must be greater than 0, right? Which means that f of x2 minus f of x1 all over x2 minus x1 is greater than 0. So if x1 is less than x2, then x2 minus x1 will be greater than 0. So the denominator of this fraction up here is positive. And because the overall thing is positive, that means the numerator also has to be positive. In other words, f of x2 minus f of x1 has to be greater than 0. In other words, f of x1 will be less than f of x2. Which, you know, these two things together, this plus this, so having x1 less than x2 and f of x1 less than f of x2 implies, well, that's the definition of increasing from above, right? So x1 less than x2 and f of x1 less than f of x2 means it's increasing. The function is increasing in this interval. Okay, and that will work for any x1, x2 in that interval from a to b. So if f prime of x is greater than 0, then f of x is definitely increasing. And you go through the same kind of argument for the other two cases. Okay. Okie dokie. So let's look at just classifying intervals as increasing or decreasing. And let me find a nice looking example. Okay. So let's go with this example. F of x equals negative 2x squared plus 4x plus 3. Okay. So I get the derivative. Prime of x equals negative 4x plus 4. I want to find the critical numbers. So f prime of x does not exist. That never happens in this case. No. Where is f prime of x equal to 0 then? So negative 4x plus 4 equals 0. X equals negative 4. So it looks like x is 1. And then what I'm going to do is draw a number line. The book uses like a chart. I like to use number lines, though. I think it's easier. On the test, I'll just want you to do a number line. Don't use the table like they do in the book. So label your critical number. So I'm going to call this line the derivative line. Okay? And I'm going to label the critical number here. And then what I need are test values, signs, and then conclusions. Okay. So for the test value, you just pick any number in that interval from negative infinity to 1. So I'll pick 0. X is 0. Let me put it in a different color, if that's possible. Thank you. Okay. Plug that value into the derivative. No, I'm working with the derivative. That's what I want to look at. Okay, so that will be positive. Negative 4 times 0 is 0, plus 4 is 4. That's positive. And the conclusion there, if the derivative is positive, it is increasing. Okay. Now let's try x is 3. And I have negative 12 plus 4 is negative, so the function is decreasing. If you think about what this is, it's a parabola, right? And it's going to be going up and then back down. And a matter of fact, that critical value should just be the vertex, the x value of the vertex. This thing right here is the x value of the vertex. You could find the vertex by using those formulas, h equals negative b over 2a. Okay. Where a, b, and c are coming from this quadratic. So h negative 4 all over 2 times negative 4 is also going to be 1, right? And again, that's the x value of the vertex. If you want the y value, you just plug 1 into the function. And that'll turn out to be the max value. Okay, let's look at another one, maybe a little harder this time. So this will be x times the square root of 16 minus x squared. Okay, so first thing, it has an implied domain. 16 minus x squared has to be greater than or equal to 0 for this to work. And if you were to kind of figure out the interval for its domain, you could factor this. Then x is 4 and x is negative 4. And then we need to find where that quadratic is greater than 0, so you can do kind of this analysis. And this time I'm looking at f of x, or y if you'd rather. Do some test value and sign. So it's the same process as what you do with the derivative, finding increasing and decreasing. This just tells you if it's positive or negative. So what I'm doing graphically, geometrically, is looking at this polynomial, right? And that thing is going to be this thing here. And my analysis down here is telling me where it's above the x-axis. Okay? In other words, where this thing I just boxed in is greater than 0. Okay? The thing I boxed in yellow there. I need that to be greater than or equal to 0 because I need the stuff in the square root to be greater than or equal to 0. Okay, so test value, like negative 5. 16 minus 25 is a negative. So we don't want that interval. Try 0. 16 minus 0 is positive. Try x is 5 over here, that'll be negative. So the interval for the domain will be from negative 4 to 4. So the implied domain, negative 4 to 4. Okay? So for our derivative, that's the interval we're going to be working on. We're not the whole real numbers anymore. So let's find the derivative. Y prime is, leave x alone, take the derivative of this thing, 1/2 times 16 minus x squared to the negative 1/2 times negative 2x. And then plus, take the derivative of x, and leave the rest alone. Okay. I'm going to clean it up a bit. Find a common denominator. So on the second guy, I'll multiply top and bottom by 16 minus x squared to the 1/2. This will end up being 16 minus x squared all over minus x squared to the 1/2. And then that'll be negative 2x squared plus 16 all over 16 minus x squared to the 1/2, okay, for the derivative. Okay, I need the critical numbers. So where this derivative does not exist, that's where the denominator is equal to 0. Square both sides. And those are at endpoints, so we're not going to worry about those. We're just going to throw those in the trash. Those are at the endpoints of our domain. And then where does f prime of x equal 0? X squared is negative 16, x squared is 8, plus or minus 2 root 2. Okay. Then finally I can do my number line with my critical numbers. And I'm testing everything in f prime of x. And maybe I should put this in brackets so we know it's going from -4 to 4. I don't accidentally put something in there I can't. Okay, so now I need my test values, my signs and conclusions. And I'll do this in red. Okay, so a lot of junk going on there. So I have to find something in this interval that's... So what is 2 root 2? That's a good question. On my calculator, I can tell you that. 2 times second root 2 is 2.82 something. So if I try -3, that'll work. Okay. So the denominator will always be positive. It has to be. It's a square root. If I put -3 in so I'm thinking about this guy right here. Okay, that's my derivative. So I put -3 in the numerator, it'll be -2 times 9. -3 squared is 9. -2 times 9 is -18, plus 16 is a negative. Okay, so it's going to be negative. In other words, it's decreasing. Try x is 0. Put 0 in there. That's clearly 0 plus 16 is 16. It's positive, so it's increasing. And then finally try 3. And again, that'll be negative, so it'll be decreasing. Okay. Okay. From this analysis, you can tell then there's going to be you can kind of see the shape of the graph in the arrows, right? Let me put it maybe in yellow. So it's going down, and then at the critical number, it's turning and going back up. And then at this critical number, it's turning and then going back down. So there's going to be a min here, and then a max at this other critical point. So you want to make that rigorous, or at least put it into our dictionary of notes here. And it's called the first derivative test. So you can tell if you have a max or a min at a critical point by looking at how the function is increasing and decreasing. Okay, so the first derivative test, and it's theorem 4.6. I'm just going to draw it in pictures. Okay, so if you're doing your graphical analysis on f prime, just like we did above, and you have a critical number here, and you have a negative and then a positive, in other words, it's decreasing, then increasing, you're going to have a min at C. So relative min at C, kind of f of C. Okay. So the second case then, if it's going up then down, on your number line, so plus and then minus, so going up and then down, then you're going to have a relative max. So you're going to be the king of the hill at C, comma f of C. The third case is where it goes minus, minus, or plus, plus. And in those cases, it's neither. Okay? So you'll have a minus, minus, or you'll have a plus, plus on your number line, and that means neither. Relative max or relative min. Okay, so let's look at a cubic. So parabolas are kind of boring. It's always going to be plus, minus, or minus, plus. And then the max or the min will be at the vertex. But, okay, so we need the critical values. Okay. So clearly this thing never exists, or never has a problem with not existing. So no. And then where does f prime of x equal 0? Divide by 6. Factor it, hopefully. So it has to be plus minus. We want the big one to be positive. And then our critical number is -2 and 1. Okay. Go to our number line. I need test values, signs, and conclusions. I'll do this in red. So I'll try x equals -3. And I'm going to plop that value, my test value, into this guy here because it'll be easier on my brain to evaluate it. Right, so if I put -3 in there, it's -3 plus 2 is a negative. -3 minus 1 is a negative. A negative times a negative is positive, so it's going up. Try 0. 0 plus 2 is positive. 0 minus 1 is negative. Positive times a negative is negative, so it's going down. Try x is 2. 2 plus 2 is 4, it's positive. 2 minus 1 is positive. Positive times a positive is positive, so it's going back up. Okay. And then from the first derivative test, we know then that -2 is going to be a max, the location of a max, and 1 is location of a min. So there's a relative max at -2 comma f of 2, whatever that is. If you plug in, you're plugging this -2 into this function right here, f of x. Okay? So if you plug -2 in there, you're going to get what is that? 20. Okay. And then there's going to be a relative min at 1 comma, plug 1 in there, 2 plus 3 is 5, minus 12 is minus 7. Okay. Okay, that's the idea. Let's look at maybe 1 or 2 more, and then we'll call it quits for this section. Okay, so f prime of x is, bring down to 2/3, x squared minus 4, 2/3 minus 3/3 is minus 1/3, and then times 2x. Okay. And then let's clean it up a little. So 4x all over x3 times x squared minus 4 to the 1/3. And then f prime of x does not exist when the denominator is 0. So 3x squared minus 4 to the 1/3 is equal to 0. Clearly that's the places that are, the x values that will make that 0 be plus or minus 2. Okay. And then I look for where f prime of x is equal to 0. So this time I take the numerator and set it equal to 0. So x will be 0. Okay. So I label my critical numbers on my derivative timeline, so to speak. So I have -2, 0, 2, and then I need my test value, my sign, and my conclusion, and I'll do that in red. Ready? Okay, so I'm plopping all of this into this formula here. So x equals -3. In the numerator, I'll have a -3 times 4 is negative. In the denominator, I'll have 3 times 9 minus 4 is positive. And then the cube root of a positive is positive, and then 3 times a positive number is also positive. So I have a negative over a positive, which would be negative, so it's going down. Try -1. In the numerator, it'll be negative, and the denominator, the determining factor will be the x squared minus 4 part. So that's, in this case, it'll be negative. So it'll end up being a negative over a negative, which is positive. So it'll be going up. I'll try x is 1. So that'll be a positive over a negative. So that'll be negative. That'll be going down. And then finally, x is 3. That'll be a positive over a positive. So that'll be going back up. Okay. So it looks like we have a relative, I put this back in white, a relative min at -2 comma f of -2. So if you put -2 back into the original function, you'll get 0. So I'm plugging it back in here above. -2 squared minus 4 is 0, so this will be 0. And also at 2, 0. Okay, and then you have a max, a relative max, at 0. Right? So it'll be 0 comma 4 to the -4 to the 2/3. Sorry, I must have a mistake in my notes. Yeah, -4 to the 2/3. Yeah, that's it. Okay. I don't know how I screwed that up in my notes. I should fix that. Let me fix that. Right, there's that. Let's look at one more. So f of x is 3 minus x times e to the x minus 3. Okay. I'm going to rewrite it so I could use, take the derivative maybe a little easier. Minus x e to the x minus 3. Prime of x, what do we have? 3e to the x minus 3 times the derivative of x minus 3 is just 1. Minus, leave the x alone. The e to the x minus 3 times the derivative of x minus 3 is just 1. And then minus, take the derivative of x is just 1 times e to the x minus 3. So combined like terms, I'll have 2e to the x minus 3 minus x e to the x minus 3. Okay. Where does this not exist? Well, never. Exponential is hard to break, so no. Where does this thing equal 0? Factor out an e to the x minus 3, and you'll have 2 minus x. That exponential part will never be 0, but the 2 minus x can be, so I'll just write 2 minus x equals 0, and then x equals 2. So our only critical number is at 2. And then I need to do my test values and all that good stuff. So my test value, my sign, my conclusion, and then I'll do that in red. Okay, I'm going to work with this version of the derivative because the exponential will always be positive, whatever I put in for x, and so I have to worry about 2 minus x for the sign. So 2 minus 0 is positive, so it's going up. Try 3. 2 minus 3 is negative, so it'll be going down. And we'll have a relative max then at 2 comma, and then I have to go back to the original function and put 2 in there. So 3 minus 2 is 1, and then e to the 2 minus 3, negative 1. E to the negative 1 will be the maximum there. Okay. Okay, so that will do it for 4.3. Again, thank you for watching, and we'll see you next time.